Hi, I'm Mr. Cotter.
And I'm Miss McNally, and we're here today to talk about the Flying Tennis Ball Project.
So let me tell you what we're going to do today. You're going to go outside with a tennis ball. You are going to throw that tennis ball up in the air as high as you can while your friend or classmate has a stopwatch, times exactly how long it takes for that tennis ball to release from your hand and hit the ground. With that information alone, you are going to figure out the maximum height at which the tennis ball traveled, and also how fast the ball was thrown when you released it. Okay. Now, at first glance, this is absolutely impossible. And the truth is, it is impossible. It is impossible with the current level of knowledge that you have, which is why we need to learn about quadratic equations.
For the purpose of this project, we need to figure out x and y. So x always being the time and y always being the height. We're given that half the force of gravity is -16, so A equals -16. B we'll need to solve for, and C will be our height in feet. Step 1 of this assignment is to collect your data.
And Ms. McNally, the first piece of data they already have. They don't need to do anything. The first piece of data is how high is the ball when you release it. Now, just for the purpose of this project, to keep it simple, we're going to assume that you release the ball at the height at which you are. So, for instance, if you are 6 feet tall, right, that initial height is 6.00. The other piece of data is the only piece of data that we're going to have to go out and collect, and that is what I just spoke about, where you're throwing the tennis ball up in the air, and we want to know how long does it take, or how much time has elapsed from when you release that tennis ball to when that tennis ball hit the ground.
It's important that both these pieces of data are rounded to 2 decimal places to get the most accurate data. Step 2, determine your y-intercept. So this is for the moment right before you release the ball.
All right. Yeah, so think about, what does the y-intercept mean in real life? And Ms. McNally said it best. That's the moment right before you release the ball. So keep in mind, every single data point that we're dealing with has an x-coordinate which represents the time, and has a y-coordinate which represents the height. So that moment that Ms. McNally is talking about, when you first release the ball, what is that x value? What is the y value? What does that mean in real life? And if you can answer those 3 questions, then step 2 is complete.
Step 3 will determine the x-intercept. This is for the moment that the ball hits the ground.
All right, so think about that again. The ball has traveled through the air and has hit the ground. And now remember, for every point, once again, there's an x-coordinate representing time, there's a y-coordinate representing height. So you've got to ask yourself, what is the time and what is the height when that ball hit the ground? And if you can say those 2 things in the real life meaning of that point, you're ready to move on to step 4.
Step 4, determine the initial speed that the ball was thrown in the air. And this is in feet per second.
All right, so for this, you got to do some math. There is no way around it. Now, Ms. McNally has already told us, right, with our equation, just to review a little bit here. You're looking at your equation on your paper right now. You're seeing x's, you're seeing y's, you're seeing a, you're seeing b, you're seeing c. Well, let me tell you, if you can break it down so make it so there is only one variable, you can always solve for that variable. That is what we call the golden ticket of mathematics, right? If you only have one variable in an equation, you can always solve for that variable. So let's talk about what Ms. McNally has already told us from the first page, right? Do we have a value for A? We do. It's -16. It represents half the acceleration of gravity, right? Do we have a value for B? No, we don't, not yet. Do we have a value for C? Yes. C is your height, or in other words, where that ball was initially released. And do we have an XY pair that we can plug in? And the answer is we do. Specifically, you got that x-intercept when that ball hit the ground. There's an x, there's a y. You plug those in. You got one variable left. It's b. You can solve for b, and what b represents, that is your initial velocity.
Step 5, rewrite your standard form quadratic equation with your values for x and y. You should now have the numbers for a, b, and c, and x and y should be your only variables.
So folks, this step is incredibly easy. All you need to do is you just need to rewrite your equation, plug in your numbers for a, b, and c, leave x and y alone. You've got your equation, and you are done with step 5.
On to step 6, we're going to create a data table, and we'll use our equation from step 5. Creating a data table will allow us to plug in values for x and solve for y.
All right, folks, this is something you guys have been doing since before you ever started algebra, just plotting points, making a data table, plugging in x, and solving for y. Now, there is one point, Mr. McNally, which will be more important than any other point we're going to talk about later, right? And that is when that ball stops going up and starts going down. You're going to start to see that as you fill out your data table. You're going to start to see where that is.
Awesome. Step 7. Given those points in step 6, we're going to make a graph. When you graph, you should see the parabola that Mr. Cotter is talking about, and you should be able to identify a vertex that is most correct.
So all we're doing here, folks, is we are just plotting points. Now, plotting points is actually the easy part of this. What students seem to have more trouble with, actually, Ms. McNally, I noticed, is scaling the graph. Right? So typically in math class, you're given a graph that's already scaled for you. When we're doing real-world math, you've got to scale your own graph. So let's just think, what does x represent? X represents time. Right? From my experience, Ms. McNally, nobody has ever taken more than 4 seconds to throw the ball further. So think about that. I think there's maybe 12 little boxes. If every 2 is a second, I think that works out. Right? And then your y-axis is going to be different for everybody. Because some of you guys, the ball may have gone, I don't know, just 10 feet up in the air. Others, maybe the ball is 100 feet up in the air. So what you're going to have to do is you're going to have to figure out the appropriate way to scale the graph so that that vertex or that highest point remains on your graph.
And don't be afraid to ask your teacher for help on this step, because you've done a lot of really awesome work on this project, and this would be really seeing what the equation looks like. So it's important to have it be accurate. Step 8, we're going to estimate our vertex. So we can guess our vertex from the data table, and we can also guess what it is from the graph. But to really get a good understanding of what that exact value is, we can use our formula to do it. What's the formula, Mr. Cotter?
Is that step 9?
That is step 8.
Step 8.
Yeah.
So using the formula, remember this, negative b over 2a. Now some students, the formula is they start to go cross-eyed, but remember, all a formula is you're trading numbers for letters. So the negative b over 2a, right, that's going to get you the x-coordinate of the vertex, right? And to get the y-coordinate, well, anytime you have an x, you can get y just by plugging that value into the equation. Right? So negative b over 2a is going to get you the x-coordinate of the vertex,
yep.
And then plugging that value into the equation is going to get you the y-coordinate of the vertex.
So solving for that actual vertex is step 9. So in step 8, we'll estimate using our data table and our graph, and in step 9, we'll do what Mr. Cotter just said. Plug in our values for b and a, and solve for what that x value of the vertex will be. Can we solve for the y value?
So we solve for the y value, right, by plugging in the x value to the equation. Yeah, absolutely.
And that'll give us our actual vertex.
That is 100% correct, Mr. McNally. So ladies and gentlemen, just remember, there's no better way to keep it real than with real-world algebra.
That's it.